Okay, so now we get to the big deal. Hybridized atomic orbitals. This is going to be a slightly longer video. It's very foundational for what we're going to be studying. We got this in Principles 2, Chem 2, Gen Chem 2, but we didn't make much of it, and we need it here. All right, so we know that methane, so here we know that methane is CH4, and we know that bonds come from the sharing of electrons, right? And we know that the orbital diagram of carbon is here, right? 1s2, 2s2, 2p2, right? But this does not explain how carbon can make 4 bonds. So when we made methane, CH4, we made it with 4 bonds. We made 4 equal bonds, and we learned that the angles between all of them were 109.5 degrees, right? So how is this possible? Well, hybridization is how this is possible. What happens is you're going to get the valence electrons here, that is the electrons in the 2 shell, right? You see all those there? Those guys, these 4 orbitals are actually going to mix, okay? So what they do is they hybridize. Oops, lost my page, okay? Now, I'm not going to say much about this down here. I'm just going to go ahead and say, let's go on to the next slide and say, oops, sorry about that. They mix, all right? So look at these. You've got your 4, 2 orbitals, right? 2s and 3 2p's, and they all mix to make a mixture. And if you get 1s and 3p orbitals, you're going to get 4 sp3 orbitals, okay? So that's the notation we're going to use. It's sp3 because we took 3 p orbitals and 1 s orbital, mixed them all together. So that's why we call that sp3. And now you can see we're ready to bring, watch this, a hydrogen in. Let me come over here, go into my draw mode, a red marker over here, and suppose if I've got a hydrogen with 1 electron, you can see that it's ready to mix with that orbital of a carbon atom, right? And here's another hydrogen ready to mix there, and we get 4 of them, right? And that's how we get CH4. Right? Okay. So, and we get that because of hybridization. Now, it turns out that the hybridized orbitals, not only do we have the molecular orbital theory version of that, but we also think about the valence bond theory about how what's the orbital going to look like, right? And remember, a p orbital had 2 lobes. One, we might have had a red lobe and a blue lobe over here, but they were equal, right? And a p looked kind of like this, right? And an s orbital was spherical. So if we mix these 2 together, this is what we get. We get a bigger lobe over here, and a smaller lobe over here. Okay, so the shape of the sp3 orbital represents, it comes from the fact that it's got 25% s character, right? Because we had 4 of these. We had 3 of those, right? We had 3 of these, and we had 1 of these, right? And so it was 75% p, and I don't know if I said that right. 75% p, that's what the 3 out of 4 means, and then 1 out of 4 is 25% s, okay? So we're going to talk about s character and p character to help us get to help us make some qualitative assessments about these orbitals, okay? Now, the hybridized orbitals, as I sort of indicated before with my molecular orbital diagram, they mix like that, right? They're ready to mix now. So you've got an sp3 orbital here, an sp3 orbital here that's ready to mix. You see that? Ready to mix and make bonds. And that's how we get our 109.5 degrees. All right. So now let's consider something that makes 3 bonds instead of 4. Well, if we make 3 bonds instead of 4, then what we're going to do is we need, right, with ethylene, which is, you can see it's C2H. Let me get my marker over here. Ethylene, you can see it's C2H4, right? And it looks like this. Got a sort of a better picture of it laying on a table right here, okay? That makes 3 bonds, and they're all about 120-degree bond angle between them, okay? Now, how does it make 3 bonds? Well, it makes, this is a double bond, by the way, but these 2 bonds are not equal, okay? There's a single bond, there's a sigma bond here and a different bond, which we talked about sigma a minute ago, but all right. Now, look at this. The way we do that is we take 2 p orbitals and 1, and we mix those to make, and can you see that these, if we're mixing those, these are 2 parts p and 1 part s, okay? And then we have this one, which remains unmixed, or unhybridized, okay? And I knew I needed 3 because I had 3 bonds up here. Let me repeat that. I knew I needed 3 because I had 3 bonds. We'll be doing this over and over and over again this semester, okay? Each carbon in ethene, or ethylene, must bond to 3 other atoms. So that's where we get these 3 bonds. That's why we need these 3 bonds, and that's why we pull those out, okay? Now, an sp2 hybridized carbon is going to have 3 equal energy sp2 orbitals, which we saw in the last slide, and 1 unhybridized p orbital, which we saw in the last slide. Okay, so here's our unhybridized p orbital, and here are our sp2s. Okay, now the shape of the sp2 orbitals results from having 33% s character, right? Because if it's sp2, can you see that we've got it? We took 1 of these and 2 of these, right? So it looks like it's 1/3 s character, and that's what this means. 1/3 s character and 2/3 p character. Okay? Now, this is interesting now. Now, in order for ethene, CH2, let me draw this back over here again. In order to make that, we're going to get 1 end-to-end overlap, which is our sigma bond, right? And then we're going to see something really neat with these guys over here. Okay, so first of all, the sp2 atomic orbitals overlap to form a sigma bond, and the p orbitals here overlap to form a pi bond, and they overlap from side to side. This is really weird looking. Okay, we're going to get some kind of an overlap here. We'll see this on the next slide, which makes like a hot dog, kind of, or a kidney bean or something like that. Okay, and that is another bond. That's a pi bond. Okay, so the pi bond is formed by side-to-side overlap, as I said in the previous slide. We'll indicate it here by seeing those bubbles overlap. Can you see these red bubbles overlap? It's side-to-side right now, right? And since it's side-to-side, we call it a pi bond. The pi bond is spread out above and below the plane in the molecule as shown. Pi bonds are weaker than sigma bonds. I think in this next slide, yeah, we got a picture right there's our little hot dog right there. That's the mixing of the side-to-side. Okay, so I took an unhybridized P and an unhybridized P, and I overlapped them side-to-side. We did this in Chem 2, but we didn't do it much, so it's important to come back and consider it deeply now. All right. Now, if we're doing acetylene, which is a triple bond, then we're only, this carbon right here, this carbon is only bonded to 2 other atoms, right? It's bonded to a hydrogen and a carbon, right? So since he's bonded to only 2 other atoms, then it's going to require the mixing of an S and a P, right? So if it's one sp, I'm sorry, if it's a 1 s orbital and 1 p orbital, then we're going to call it an sp hybridized, okay? And can you see how these 2 here got converted to make the hybridized orbitals, where they're 2 equal energy or degenerate sp orbitals, and these 2 remain unhybridized, okay? So what's that going to look like? Well, the hybridized, right, are here, here, and here, right? So the hybridized orbitals, I was only looking at 1 carbon at a time, so look at, I had a sp hybridized orbital over here, sp hybridized orbital over here, and it mixes with, you got an sp here and an sp here. These 2 mix to make another sigma bond, right? Can you see that? You can't, it's difficult to see. Yeah, there's the arrow right there. I overwrote it. Let me get rid of that. Can you see that this sigma bond is pointing down to this end-to-end overlap right there? Okay? And these reds are going to overlap side to side to make a pi bond. And can you see that there's going to be another pi bond that goes this way? Okay. And so this carbon is going to make one sigma bond. Let me make this in black here. That's a sigma bond, and that's the side-to-side or the end-to-end overlap right there, right with the hydrogen. That's what that is. And it's going to make another sigma bond here, right? And that's that end-to-end overlap. And then it's going to make a pi bond. Lost my marker here for a second. It's going to make a pi bond, which is maybe that one right there, right, a side-to-side overlap, and then another pi bond, okay? So this triple bond is actually made up of a sigma and two pi's, okay? And here is another sigma bond because it's end-to-end overlap, okay? All right. So finally, let's talk about the length and strength of these bonds. So this bond here is made up of, let me come here in red, this bond is made up of an sp3 hybridized atom and another sp3 hybridized atom because they have 4 identical bonds, right? And so that bond, the bond itself is made up of an sp3. This bond is made up of an sp2 hybridized atom because it's got 3 bonds to it, right? sp2, how do you spell 2? Right? That's what that bond is. And this bond is made up of 2 atomic orbitals, which were sp hybridized, right? So since this has the most p character, this is 75% p. It's going to be the longest, right? It's going to be the longest and the weakest. See that? Okay. This is only, looks like this has got 2 parts P and 1 part S. So this is 66% or 67%, I guess, P character. And so it's going to be shorter, right? And this one is only 50% P character, right? Because it was SP. It was 1 S and 1 P that came together. 50% P character, which is going to make it the shortest. And as you can see, the strongest. Okay? So this will make more sense as we practice it more. But this is our briefest introduction to hybridized atomic orbitals, making molecular orbitals that we can do.